Hi everybody, Professor Jamer here, and today we're going to be talking about topic 15, which is essentially a continuation of forces. And so whenever we looked at topic 14, we introduced Newton's second law, which is essentially whenever we look at the net forces acting on an object, it's going to be equal to the mass times the acceleration. So let's just say we have a block on the floor and we're neglecting friction for right now until we learn about it in topic 16. And what we have is that this is the center of the box. And so we know that there's the force due to gravity right here. And then we know that there's a normal force. So if we're pushing on the block, we're going to have an applied force that is going to be pushing it to the right. Even though we're probably applying the force back here, we always draw the forces from the center of the object. And so whenever we are looking at this diagram, we know that there's going to be an x and a y component. So if we were to look at the y component, what we would have is F net y is equal to MAY. And since the block is staying on the floor, there's no acceleration in the y component. So now what we have is that the normal force minus the force due to gravity is equal to 0. And so we can take this a step where we have the normal force minus mg is equal to 0. So the normal force has to equal the weight of the box. And then we can have F net x is equal to max. Here in the x direction, since we're neglecting friction for right now, the F applied is going to be equal to the mass times the acceleration in x. So here is where we have Newton's second law, and we split everything up in terms of components in order to solve problems. So in Newton's second law, we have F net. F net is the vector sum of all physical forces on the object, and we know F net is equal to MA, which is the most important thing that you'll learn in physics, because you're going to be using this in physics, and if you are an engineering major, then essentially you're going to cover F is equal to MA in statics and dynamics. And so we have components max and may in order to solve for all the different forces and balance everything. So here we have a view of a box. We have two people pulling on it. The ropes have tension, so we have two tensions, and we can figure out the directions of the acceleration if we were to add up the vectors, and then we can figure out that here acceleration is going to be a vector. So we kind of covered this in topic 14 already. So for Newton's first law, it's basically saying that an object in motion wants to stay at motion, and the object at rest wants to stay at rest. And so we've all heard that before. So an object at rest likes to stay at rest, and an object in motion stays in motion. And so it stays at the same speed and in the same direction unless it's acted upon by an unbalanced force. So basically, Newton's second law only works in inertial reference frames. So here we think about, okay, so we might have a system where we're on an airplane and we have a drink resting on the little tray table, and we know that the plane is moving, but we kind of close that system just on that drink and that tray table, because otherwise we're not going to really look at physics in the same way. So essentially, we're always taking into account the inertial reference frame. All right. Next slide. So now an example problem. So if we were trying to figure out F net of an elevator, what we know is that F net y is equal to MAY. So we know that if we have an elevator, there's going to be a tension rope that is causing it to accelerate either upwards or downwards, depending on the directions that it's moving. So in this case, we have tension of the rope and we have the force due to gravity, and we're assuming that the force is going up. So here what we have is T minus Fg is equal to ma. So this is how we can set up a lot of these elevator problems. And whenever we're doing an elevator problem, we always want to note the direction that Fnet is going, and you'll see why in a couple of seconds. So let me switch to my notepad here. So we have a 65 kilogram person riding an elevator upward. So here's our elevator, and here's our person. And so let's just say we're only concerned about inside of the system. So the elevator is rising, so this is going to be F net is equal to MAY. We know that the person has weight, FG is equal to the mass of the person times gravity, and then we know that the person will have a normal force. So we can think about the normal force in terms of our weight. So if we were to step on a scale right now, the scale is actually measuring our normal force. So it is the amount of essentially weight that the scale has to exert on us in order to keep us from not accelerating. So we're trying to figure out how much this person weighs whenever we have the elevator accelerating upwards. So here what we have is F net is equal to MA, and we're going to say that F net Y is equal to MAY. So here in our system we have the normal force minus mg is going to be equal to MA. And we know that it's moving upwards because that's what the problem prompt says, because we have a 65 kilogram person riding an elevator upward, and it's speeding up with an acceleration of 3.7 meters per second. So here, whenever we're trying to find the normal force of the person, it's going to be the mass of the person times the acceleration plus the mass of the person times the force due to gravity, or we can simplify it and say it's ma plus g. Now we can plug in our variables, and we know the person's 65 kilograms, they're moving with an acceleration of 3.7, and we know the force due to gravity on Earth, which is 9.8. So then what we have is 3.7 plus 9.8 times 65. So this person's normal force, whenever the elevator is moving, is 877.5 newtons. So now, let's think about it when the person's not moving. So does the scale read higher or lower than when they're not moving? So if the person's not moving, we remove this F net. So we just have the normal force of the person, and then we have mg in terms of the scale. And so we would have N is equal to mg. So we have 65 times 9.8. So the person actually weighs 637 newtons. So whenever we're comparing, if the person's moving upwards in the elevator and they're accelerating upwards, then we're going to see that they weigh more than if they were just standing still on the elevator that isn't accelerating. So now let's take a quick look at the second part of the problem. So what is the tension in the elevator's cable? So we see that the combined mass of the elevator and the person is 620 kilograms. So what is the tension in the elevator's cable? So here for part B, we're looking at the entire elevator, which has with the person in it. And we called the person's mass little m, so let's call this whole system's mass big M. So here, we don't have a normal force because we have the tension. So we only have normal force whenever if the elevator was on something that was exerting a force on it. So let's just say the elevator was being pushed up by, something like a forklift or something. Then we would have the normal force. But since we have tension and the elevator is kind of just hanging off of that rope, we don't have a normal force. So now we have, this is going to be m times g. And then we have the acceleration is going to be equal to 3.7 meters per second squared. So now let's find the tension in the elevator's cable. So essentially we're doing the same thing where we have F net acting only in the y, and then we have it equal to MAY, and our two forces is the tension and the mass times the gravity of the elevator, so the gravitational force. So then the tension is going to be equal to the mass times the gravitation plus the acceleration. And so whenever we calculate this, we have 620 kilograms from the problem prompt. So that's 620 times 9.8 plus 3.7. So then we get a tension in our elevator cable of 8,370 newtons. So this is how you can do these types of problems in one dimension. And we have a couple of them for you to do on the worksheet and in your homework. So if you have any questions, please reach out to me. But essentially, topic 15 is essentially just this. Thanks for paying attention.